Chapter 5 Video and Animation Learning Objectives. In this chapter, the users would learn the following aspects of video and animation. Video basics, how video works, broadcast video standards, analog video, digital video, video recording and tape formats, shooting and editing video, video compression and file formats, video compression based on motion compensation, MPEG-1, MPEG-2, MPEG-4, MPEG-7, MPEG-21. Animation, cell, animation, computer animation, morphing. Introduction to video compression. A video consists of time-ordered sequence of frames, that is, images. An obvious solution to video compression would be predictive coding based on previous frames. Compression proceeds by subtracting images. Subtract in time, order, and code the residual error. It can be done even better by searching for just the right parts of the image to subtract from the previous frame. Video compression with motion compensation. Consecutive frames in a video are similar temporal redundancy exists. Temporal redundancy is exploited so that not every frame of the video needs to be coded independently as a new image. The difference between the current frame and other frames in the sequence will be coded. Small values and low entropy, good for compression. Steps of video compression based on motion compensation, MC. Motion estimation, motion vector search, MC-based prediction, derivation of the prediction error, that is, the difference. Motion compensation. Each image is divided into macro blocks of size n into n. By default, n equals 16 for luminance images. For chrominance images, n equals 8 if 4:2:0 chroma subsampling is adopted. Motion compensation is performed at the macro block level. The current image frame is referred to as a target frame. A match is sought between the macro block in the target frame and the most similar macro block in previous and/or future frames, referred to as reference frames. The displacement of the reference macro block to the target macro block is called a motion vector, MV. Sequential search. Sequentially search the whole 2p plus 1 into 2p plus 1 window in the reference frame, also referred to as full search. A macro block centered at each of the positions within the window is compared to the macro block in the target frame, pixel by pixel, and the respective MAD is then derived by using the vector I, j that offers the least MAD is designated as the MV, U, V for the macro block in the target frame. Sequential search method is very costly. Assuming each pixel comparison requires 3 operations, subtraction, absolute value, addition. The cost for obtaining a motion vector for a single macro block is as seen on the screen. 2D logarithmic search. Logarithmic search, a cheaper version that is suboptimal but still usually effective. The procedure for 2D logarithmic search of motion vector takes several iterations and is akin to a binary search. Initially, only 9 locations in the search window are used as seeds for a MAD-based research. They are marked as 1. After the 1 that yields the minimum MAD is located, the center of the new search region is moved to it and the step size offset is reduced to half. In the next iteration, the new 9 locations are marked as 2 and so on. Hierarchical search. The search can benefit from a hierarchical, multi-resolution approach in which initial estimation of the motion vector can be obtained from images with a significantly reduced resolution. A 3-level hierarchical search in which the original image is at the level 0, images at levels 1 and 2 are obtained by downsampling from the previous levels by a factor of 2, and the initial search is conducted at level 2. Since the size of the macro block is smaller and P can also be proportionally reduced, the number of operations required is greatly reduced. A glance at syntax of H261 video bitstream. A hierarchy of 4 layers. Picture, group of blocks, GOB, macro block, and block. The picture layer, PSC, picture start code, delineates boundaries between pictures. TR, temporal reference, provides a timestamp for the picture. The GOB layer, H261 pictures are divided into regions of 11 into 3 macro blocks each of which is called a group of blocks, GOB. Figure depicts the arrangement of GOBs in a CIF or QCIF luminance image. For instance, the CIF image has 2 into 6 GOBs, corresponding to its image resolution of 352 by 288 pixels. Each GOB has its start code GBSC and group number GN. In case a network error causes a bit error or the loss of some bits, H.261 video can be recovered and resynchronized at the next identifiable GOB. Gquant indicates a quantizer to be used in the GOB unless it is overridden by any subsequent mquant quantizer for macro block. The macro block layer. Each macro block MB has its own address indicating its position within the GOB, quantizer mquant, and 6 8x8 image blocks, 4Y, 1CB, 1CR. The block layer. For each 8x8 block, the bit stream starts with DC value, followed by pairs of lengths of 0 run, and the subsequent non-zero value, level for ACs, and finally the end of block, EOB code. The range of run is 0, 63. Level reflects quantized values. Its range is -127, 127, and level equals 0. H.261. H.261, an earlier digital video compression standard, its principle of MC-based compression is retained in all later video compression standards. The standard was designed for video phone, video conferencing, and other audiovisual services over ISDN. The video codec supports bit rates of P by 64 kbps, where P ranges from 1 to 30, hence also known as P64, require that the delay of the video encoder be less than 150 milliseconds so that the video can be used for real-time bidirectional video conferencing. ITU recommendations and H.261 video formats. H.261 belongs to the following set of ITU recommendations for visual telephony systems. H.221, frame structure for an audiovisual channel supporting 64 to 1920 kbps. H.230, frame control signals for audiovisual systems. H.242, audiovisual communication protocols. H.261, video encoder-decoder for audiovisual services at P by 64 kbps. H.320, narrowband audiovisual terminal equipment for P by 64 kbps transmission. H.261 frame sequences. Two types of image frames are identified: intraframes, I-frames, and interframes, P-frames. I-frames are treated as independent images. Transform coding method similar to JPEG is applied within each I-frame, hence intra. P-frames are not independent. Coded by a forward predictive coding method. Temporal redundancy removal is included in a P-frame coding, whereas I-frame coding performs only spatial redundancy removal. To avoid propagation of coding errors, an I-frame is usually sent a couple of times in each second of the video. Motion vectors in H.261 are always measured in units of full pixel, and they have a limited range of plus or minus 15 pixels. That is, P equals 15. Intraframe, I-frame coding. Macro blocks are of size 16 by 16 pixels for the Y-frame and 8 by 8 for CB and CR frames, since 4:2:20 chroma subsampling is employed. A macro block consists of 4 Y, 1 CB, and 1 CR 8 by 8 blocks. For each 8 by 8 block, a DCT transform is applied. The DCT coefficients then go through quantization, zigzag scan, and entropy coding. Interframe, P-frame, predictive coding. The H.261 P-frame coding scheme based on motion compensation. For each macro block in the target frame, a motion vector is allocated by one of the search methods discussed earlier. After the prediction, a difference macro block is derived to measure the prediction error. Each of these 8 by 8 blocks go through DCT, quantization, zigzag scan, and entropy coding procedures. Quantization in H.261. The quantization in H.261 uses a constant step size for all DCT coefficients within a macro block. If we use DCT and QDCT to denote the DCT coefficients before and after the quantization, then for DC coefficients in intra mode, the representation will be as seen in the screen. H.261 encoder and decoder. A scenario is used where frames L, P1 and P2 are encoded and then decoded. Note, decoded frames, not the original frames, are used as reference frames in motion estimation. The data that goes through the observation points indicated by the circled numbers. Video basics. Video is the most recent addition to the elements of multimedia. It places the greatest demands on the computer and memory, using about 108 GB per hour for full motion. Often requires additional hardware, video compression board, audio board, RAID, redundant array of independent disks for high-speed data transfer. Digital video device produces excellent finished products at a fraction of the cost of analog. Digital video eliminates the image degrading analog to digital conversion. Many digital video sources exist, but getting the rights can be difficult, time-consuming, and expensive. Video clips. Ways to obtain video. Shoot new film clips with a digital camcorder. Convert your own video clips to digital format. Acquire video from an archive, often very expensive, difficult to obtain permissions or licensing rights. How does a video work? Light reflected from an object through the camera's lens is converted into electronic signal by charge-coupled device, CCD. This electronic signal contains 3 channels of color information and synchronization pulses, sync. Several video standards exist that deal with the amount of separation between the components of the signal. Transmission mode. Composite video yields less precise color definition. Colors cannot be manipulated or corrected. A coaxial cable or RCA connector is usually used. S-video. S-video cables use a unique S-video connector. Component video. 2 chrominance and 1 luminance signals. Chrominance equals information on colors. Luminance equals information on brightness. The video signal is magnetically written to tape by a spinning recording head following a helical path. Audio is recorded on a separate straight track. The control track regulates the speed and keeps the tracks aligned as the tape plays or records. Color encoding for video transmission. RGB signal consists of separate signals for red, green, and blue. Other colors can be coded as a combination of these primary colors. For example, white equals R plus G plus B. YUV signal. Separate brightness, luminance component Y. Color information, 3 chrominance signals U and V. Y equals 0.3 R plus 0.59 G plus 0.11 B. U equals B minus Y into 0.493. V equals R minus Y into 0.877. YIQ signal, similar to YUV. Basis for the NTSC format. Y equals 0.3 R plus 0.59 G plus 0.11 B. I equals 0.60 R minus 0.28 G plus 0.32 B. Q equals 0.21 R minus 0.52 G plus 0.31 B. Composite signal. Individual component RGB, YUV or YIQ must be combined into one signal. Broadcast video standards. 4 broadcast and video standards and recording formats commonly used around the world are NTSC, PAL, CCAM, High Definition Television. Each system is based on a different standard that defines the way information is encoded to produce an electronic signal that ultimately creates a television picture. National Television Standards Committee, NTSC. These standards define a method for encoding information into electronic signal that creates a television picture. It has screen resolution of 525 horizontal scan lines and a scan rate of 30 frames per second. NTSC, National Television Standards Committee, 1952. 1 frame equals 525 horizontal lines every 1/30th of a second. 2 passes, odd by even lines, 60 per second, 60 Hz. Interlacing to reduce flicker. Phase alternate line, PAL. PAL has a screen resolution of 625 horizontal lines and a scan rate of 25 frames per second. CCAM, sequential color and memory. CCAM has a screen resolution of 625 horizontal lines and is a 50 Hz system. CCAM differs from NTSC and PAL color systems in its basic technology and broadcast method. This standard is used in France, Russia, and a few other countries. CCAM video has 625 interlaced lines of resolution. Advanced Television Systems Committee, ATSC, Digital Television, DTV. This digital standard provides TV stations with sufficient bandwidth to present 4 or 5 standard television signals or 1 high-definition TV signal. This standard allows for transmission of data to computers and for new advanced TV, ATV interactive services. Analog video. Overscan and the safe title area. Analog television sets remain the most widely installed platforms for delivering and viewing video. Overscan occurs when an image is larger than the standard TV screen. Underscan occurs when computer monitors display a smaller image on picture tube. The safe title area is where the image will not be affected by overscanning, even in the worst conditions. Video color. Computer monitors use RGB color. Video uses YUV color. A YUV signal includes separate red, blue, and luminance brightness information. Many RGB colors will not display in the YUV color space. High-end video editing applications offer filters to help you identify and correct illegal RGB colors in the YUV color space. Interlacing effects. Interlaced and progressive scanning. Television uses interlaced scanning. Computer employs progressive scanning. Interlacing effect. Lines that are 1 pixel thick will flicker on a TV due to interlacing. Make sure fonts and other lines are thicker than 1 pixel. Text and titles for television and taking care of analog tapes. Use plain sans serif fonts. Use light text over a dark background. Do not kern the letters too tight. Remember to avoid single pixel thick lines. Avoid parallel lines, boxes, and tight concentric lines. Keep the graphics and title within the title safe area. Leave titles on screen long enough to be read. Digital video. Video clips stored on any mass storage device can be played back on a computer's monitor without special hardware. Setting up production environment for making digital video requires some hardware specifications. Some specifications include computer with FireWire connection and cables, fast processor, plenty of RAM, fast and big hard disk. To digitize a video using computer, a video capture card is required. Alternatively, the analog signal can be digitized and compressed using circuitry inside a camera. There are 2 significant advantages in using computer-based digital video: the ability to randomly access the video, the ability to compress the video. Digital video architecture. Digital video architecture consists of a format for encoding and playing back video files by a computer. Architecture includes a player that can recognize and play files created for that format. Digital video compression. Digital video compression schemes or codecs, coder, decoder, is the algorithm used to compress, code a video for delivery. The codec then decodes a compressed video in real time for fast playback. Streaming audio and video starts playback as soon as enough data has transferred to the user's computer to sustain this playback. Characteristics of digital video. A frame is a single image in a video sequence and is the same as single cell of movie film. 3 basic characteristics of digital video are frame rates, frame size, color depth or resolution. Frame rates, number of images displayed within the specified amount of time to convey a sense of motion. Frame size, the height and width of each individual frame or image. Color depth or resolution, the amount of color for each pixel within each frame or image. The size of a digital video file directly related to the frame rate, size, and color depth. Display. Cathode ray tube, CRT. Colored phosphors on a cathode ray tube, CRT, screen glow red, green, or blue when they are energized by an electron beam. Because the intensity of the beam varies as it moves across the screen, some colors glow brighter than others. Finely tuned magnets around the picture tube aim the electrons precisely onto the phosphor screen, while the intensity of the beam is varied according to the video signal. Degaussing. A strong external magnetic field can skew the electron beam to one area of the screen and sometimes cause a permanent blotch that cannot be fixed by degaussing, an electronic process that readjusts the magnets that guide the electrons. Liquid crystal display, LCD. Flat-screen displays are all digital, using either liquid crystal display, LCD, or plasma technologies, and have supplanted CRTs for computer use. Digital video compression. A digital video architecture is made up of an algorithm for compressing and encoding video and audio, a container in which to put the compressed data, and a player that can recognize and play back those files. Digital video containers. Common containers for video are OGG or OGG, Theoro for video, Vorbis for audio, Flash video, MPEG, QuickTime, Windows Media Format, WebM, and Real Media. Containers may include data compressed by a choice of codecs, and media players may recognize and play back more than one video file container format. Container formats may also include metadata, important information about tracks contained in them, and even additional media besides audio and video. The QuickTime container, for example, allows inclusion of text tracks, chapter markers, transitions, and even interactive sprites. Totally Hip's Live Stage Pro is an authoring tool that can produce interactive multimedia self-contained within a single QuickTime.mov container. MPEG is a real-time video compression algorithm. MPEG-4 includes numerous multimedia capabilities and is a preferred standard. MPEG-7, or Multimedia Content Description Interface, integrates information about motion video elements with their use. Composite analog video. Composite video combines the luminance and chroma information from the video signal. Composite video produces lowest quality video and is most susceptible to generation loss. Generation loss is a loss of quality that occurs while moving from original footage to editing master to copy. Analog video. Analog video is represented as a continuous, time-varying signal. Digital video is represented as a sequence of digital images. NTSC video. 525 scan lines per frame, 30 fps, 33.37 millisecond per frame. Interlaced, each frame is divided into two fields, 262.5 lines per field, 20 lines reserved for control information at the beginning of each field. So a maximum of 485 lines of visible data. Laserdisc and SVHS have actual resolution of approximately 420 lines and ordinary TV approximately 320 lines. Each line takes 63.5 microseconds to scan. Color representation uses YIQ color model. PAL-CCAM video. 625 scan lines per frame, 25 frames per second, 40 millisecond per frame. Interlaced, each frame is divided into two fields, 312.5 lines per field. Color representation uses YUV color model. Component analog video. Component video separates the luminance and chroma information. It improves the quality of the video and decreases generation loss. In S-video, color and luminance information are kept on two separate tracks, Y, C, to improve the picture quality. Betacam is a new portable professional video format which lays the signal on the tape in 3 component channels. Composite digital. Composite digital recording formats combine the luminance and chroma information. They sample the incoming waveforms and encode the information in binary 0, 1 digital code. It improves color and image resolution and eliminates generation loss. Component digital. Component digital formats add the advantages of component signals to digital recording. D1 component digital format is an uncompressed format which has a very high quality image. It uses 19 mm 3/4 inch tape in order to save data. Several other digital component formats are DCT, Digital Betacam, DV format, DVC Pro, and DVCam formats. ATSC Digital TV. These standards provide for digital STV and HD TV recordings that can be broadcast by digital TV transmitters to digital TV receivers. ATSC standards also provide for enhanced TV, bringing the interactivity of multimedia and the web to broadcast television. Shooting and editing video. Import video and sound at the highest resolution and with the least amount of compression possible. Resolution should be reduced and footage must be compressed later according to the requirements. A steady shooting platform should always be used. Good and even lighting is extremely important. Blue screen in digital video editing applications is a popular technique for making multimedia. Wide panoramic shots and camera motion should be avoided when shooting for a small computer window on CD-ROM or the web. Optimizing video files for CD-ROM. CD-ROMs provide an excellent distribution medium for computer-based video. When preparing video for CD-ROM distribution, interleave the audio tracks with the video track. Keyframes should be used every 10 to 15 frames and the size of the video window must be kept small. The Sorensen codec is optimized for CD-ROM playback. Basics of MPEG. Picture sizes up to 4095 by 4095. Most algorithms are for the CCIR 601 format for video frames. YCBCR color space. NTSC 525 lines per frame at 60 fps, 720 by 480 pixel luminance frame, 360 by 480 pixel chrominance frame. PAL 625 lines per frame at 50 fps, 720 by 576 pixel luminance frame, 360 by 576 pixel chrominance frame. SIF, source input format for digital TV. Luminance resolution 360 by 240 pixels at 30 fps or 360 by 288 pixels at 25 fps. Chrominance resolution, half the luminance resolution in both dimensions. MPEG overview. MPEG-1, a standard for storage and retrieval of moving pictures and audio on storage media. MPEG-2, a standard for digital television. MPEG-4, a standard for multimedia applications. MPEG-7, a content representation standard for information search. MPEG-21 offers metadata information for audio and video files. MPEG-1 overview. First standard to be published by the MPEG organization in 1992. A standard for storage and retrieval of moving pictures and audio on storage media. Example formats: video CD, VCD, MP3, MP2. 5 parts of MPEG-1. Part 1. Combining video and audio inputs into a single or multiple data stream. Part 2. Video compression. Part 3. Audio compression. Part 4. Requirements verification. Part 5. Technical report on the software implementation of the parts 1 to 3. Processes of audio encoder. Mapping block divides audio inputs into 32 equal width frequency subbands, samples. Psychoacoustic block calculates masking threshold for each subband. Bit allocation block allocates bits using outputs of the mapping and psychoacoustic blocks. Quantizer and coding block scales and quantizes, reduce the samples. Frame packing block formats the samples with headers into an encoded stream. MPEG-1 layers 1, 2, and 3. MPEG layer differences lie in processing power and resulting audio sound quality. MP1 little processing needed, poor quality. MP2 minimal processing, okay quality. MP3 massive processing, high CD quality. MPEG-2 overview extends video and audio compression of MPEG-1, substantially reduces bandwidth required for high-quality transmissions, optimizes balance between resolution, quality, and bandwidth speed. 10 parts of MPEG-2. Part 1. Combine video and audio data into single/multiple streams. Part 2 offers more advanced video compression tools. Part 3 is a multi-channel extension of the MPEG-1 audio standard. Part 4, 5 correspond to and build on Part 4, 5 of MPEG-1. Part 6 specifies protocols of managing MPEG-1 and MPEG-2 bit streams. Part 7 specifies a multi-channel audio coding algorithm. Part 8 was discontinued because of obsolescence. Part 9 specifies the real-time interface, RTI, to transport stream decoders. Part 10, the conformance part of digital storage media command and control, currently under development. MPEG-4 overview. Submergence. Handles specific requirements from rapidly developing multimedia applications. Advantages over MPEG-1 and MPEG-2. Object-oriented coding. MPEG-4 standard 6 parts overview. Part 1, Systems, specifies scene description, multiplexing, synchronization, buffer management and protection of intellectual property. Part 2, Visual, specifies the coded representation of natural and synthetic visual objects. Part 3, Audio, specifies the coded representation of natural and synthetic audio objects. Part 4, Conformance testing, defines conformance conditions for bit streams and devices. This part is used to test MPEG-4 implementations. Part 5, Reference software, includes software corresponding to most parts of MPEG. It can be used for implementing compliant products as ISO waives the copyrights of the code. Part 6, Delivery Multimedia Integration Framework, DMIF, defines a session protocol for the management of multimedia streaming over generic delivery technologies. Features and functionalities. Object-oriented. Primitive audiovisual objects are coded. Low data rate. Allows for high-quality video at lower data rates and smaller file size. Interoperability. Opens methods in playing with audiovisual scenes. MPEG-7 overview. Another ISO or IEC standard being developed by MPEG. Content representation standard for information search. Makes searching the web for multimedia content as easy as searching for text-only files. Operates in both real-time and non-real-time environments. The future of MPEG-21. Multimedia framework based on two essential concepts: digital item, concept of users interacting with digital item. More universal framework for digital content protection. Most of MPEG-21's elements are set for completion in 2003 and 2004. The power of motion. Animation is defined as the act of making something come alive. It is concerned with the visual and aesthetic aspect of the project. Visual effects such as wipes, fades, zooms, and dissolves are available in most authoring packages, and some of these can be used for primitive animation. Animation is an object moving across or into or out of the screen. Principle of animation. Animation is possible because of the biological phenomenon known as the persistence of vision and a psychological phenomenon known as PHI. In animation, a series of images are rapidly changed to create an illusion of movement. Animation by computer. Animation space. Animation techniques. Animation space. Animation can be rendered in 2D space. 2D animations are very simple and static. Color cycling, 2D animation, path animation. At 2.5D space, an illusion of depth is created through shadowing, highlighting, and forced perspective, though in reality the image rests in 2 dimensions. 3D space. Complicated and realistic animations are done in 3D space. Animation techniques. Animation process, cell animation, computer animation. Animation process. The steps to be followed in creating animation are: organize the execution in a series of logical steps. Choose an animation tool best suited for the job. build and tweak the sequences by creating objects, planning their movement, texturing the surfaces, adding lights, experimenting with lighting effects, and positioning the camera or point of view. Post-process the completed animation. Cell animation. Cell animation is a technique in which a series of progressively different graphics are used on each frame of movie film. The term cell is derived from the clear celluloid sheets that were used for drawing each frame. Cell animation begins with keyframes. Keyframes refer to the first and the last frame of an action. The frames in between the keyframes are drawn in the tweening process. Tweening depicts the action that takes place between keyframes. Tweening is followed by the pencil test. Computer animation is very similar to cell animation. The primary difference is in how much must be drawn by the animator and how much is automatically generated by the software. Computer animation. Kinematics is a study of the movement and motion of structures that have joints. Inverse kinematics is a process of linking objects and defining their relationship and limits. Morphing is an effect in which a still or moving image is transformed into another. Curious Labs poser understands human motion and inverse kinematics. Move an arm and the shoulders follow. Morphing software was used to seamlessly transform the images of 16 kindergartners. When a soundtrack of music and voices was added to the 4-minute piece, it made a compelling QuickTime video about how similar children are to each other. Matching key points read in the start and end image guide the morphing transition. File formats used in animation. .dir and .dcr director files, .fli and .flc animator pro files, .max 3D Studio Max files, .pics supercard and director files, .fla and .swf flash files. GIF89, a file format. It is a version of the GIF image format. GIF89A allows multiple images to be put into a single file and then be displayed as an animation in the web browser. Applications like Boxtop Software's GIFmation or Ulead's GIF Animator are needed to create GIF89A animation. Conclusion. In this chapter, the users have covered the following aspects of video and animation. Video basics, how video works, broadcast video standards, analog video, digital video, video recording and tape formats, shooting and editing video, video compression and file formats, video compression based on motion compensation, MPEG-1, MPEG-2, MPEG-4, MPEG-7, MPEG-21, animation, cell, animation, computer animation, morphing.